Hi, everybody. We are in the middle of a really rich discussion about finding derivatives using calculus. So we found rules such as the product rule and the quotient rule, the chain rule, different ways we can find derivatives of a variety of functions. And we also talked about inverse functions, trigonometric functions. We looked at how to find the derivative of a specific inverse function, not necessarily an inverse trig function. And so this video is going to take everything a step further, and we're going to try and write derivatives implicitly. So we're going to try to solve for dy dx, which means differentiate y with respect to x. Now this dy dx, little notation, simply just means the derivative, and x is the independent variable in this expression. I've put out 4 steps for implicit differentiation. When you write a derivative, you're essentially differentiating a function. So the verb is to differentiate. The noun would be derivative. And here are the steps. We're going to differentiate both sides with respect to x, but when we come across a variable that is not an x, then we need to multiply by the chain rule piece right here, dy dx, and I'll show you how that works and why we do that in a little bit. Once we've done that, we're going to have dy dx is sort of in the formula, and we want to collect the dy dx terms on one side of the equation. Step 3, factor out the dy dx term as a greatest common factor. And then finally, step 4, we would then isolate dy dx, which would give us a resulting formula, a formula for the slopes, essentially the derivative with respect to x. Now, step 1 is the only step in this process that involves calculus. Collect like terms, factor GCFs, isolate a variable. Those are all algebra steps. So we have a lot of algebra to do in this lesson when we write derivatives implicitly. So here's an example, y cubed equals x squared, and the problem says to find dy dx. So I'm going to do this implicitly to show you how it works in this video, very basic. We're going to take the derivative of the entire expression. So 3y squared equals 2x. Now that actually is incorrect because we're trying to find the derivative with respect to x, and my first variable ended up being a y. So while 3y squared is the correct use of power rule, what I didn't write down was the chain rule component. I've got to multiply every little y piece by dy dx because I'm going to treat y as its own function, as its own sort of inside argument right here. So now it's ready to go. I have my dy dx piece, and I want to solve for dy dx. So let's isolate that by dividing by 3y squared. So dy dx is equal to 2x over 3y squared. And that's my formula for the derivative dy dx. If I wanted to find the slope of the function at a given point, notice I would need both an x and a y coordinate here to plug them in and then compute the value of the derivative. Now, explicitly would basically just mean, as I look at this equation, y cubed equals x squared, I could cube root both sides and do a little bit of algebra right here. So 2x to the 2/3 if I cube root the left and the right. And then I can very easily find dy dx. Let's find the derivative. By power rule here, it's going to be 2/3 x to the negative 1/3, and there again is my derivative. So explicitly, I'll have a derivative in terms of x. Implicitly, I may have a couple different variables within that formula. So that's sort of how implicit differentiation works. I'd like to show you some more complicated examples, and we'll do that here with the ones coming up. Now, I want you to notice in number 1, oh, by the way, let's box in dy dx. And don't forget what that means. That means the derivative of y with respect to x. That's really showing us what the independent variable is in this problem. And when we're finished, dy dx is going to be a formula for the slope of the tangent line. Or the slope, the rate of change of the relation as it exists. And these things may not be functions. We might have sideways parabolas. We could have an ellipse. Maybe we have a hyperbola. Again, a sideways hyperbola, where they're not functions. They would fail the vertical line test. But yet, using implicit differentiation, we can figure out a way to write a derivative or to find dy dx. In number 1, I actually have a product rule to start off. So I have 2x times y. Don't miss that detail. This right here is a product. So I need to go to my tool bag and find the product rule and apply it correctly here. So first component is 2x. Second component is y. Product rule says find the derivative of the first, which is 2, times the second, which is just y, plus the first, times the derivative of the second. Now, the derivative of y is going to be just 1, but because it's y, I need the chain rule piece in there, so it's going to be 1 times dy dx. So that all came from the product rule. Let's keep going. What is the derivative of y squared plus 2y? But once again, it's a y. It's not an x, so I can't just say 2y. It's 2y and then chain rule times dy dx, the derivative of the inside. And then that 3 becomes a 0 because the derivative of a constant is always 0. So there's my differentiation of the entire equation. I wrote the derivative of the left-hand side. I wrote the derivative of the right-hand side. If I go back to my chart, after we do that, my second step here said to collect the dy dx terms on one side of the equation. So, well, here they are. Let's collect them on the left-hand side, which means this 2y I would like to move out of the way. So what if we subtract 2y? I'll have 2x dy dx plus 2y dy dx equals negative 2 times y. And then we're going to factor. GCF factoring dy dx. Pull that out, and we'll have 2x plus 2y equals negative 2y. Final step, we want to solve for dy dx, because once we do that, we'll have our solution. Negative 2y in the numerator, divide that by 2x plus 2y. And let's do a little bit of factoring. So if we factor out a 2, I can cancel the 2 up here and here. So we'll have, looks like a simplified negative y over x plus y. And that is the answer. That's the derivative, dy dx. What we found was a formula. That's a formula. And I could give you, if we knew what a given x and y ordered pair was on this relation, we could plug that into our dy dx derivative formula and find the value of the slope of the tangent at that point. Look at the next example over here, problem 2. I'm going to just ask you to be very, very careful here. I'll write the word caution. Caution, because inside here we have a product rule kind of buried. So, but the product is the argument of a trig function. So, kind of a lot of details here to pay attention to. Let's begin. Chain rule. The derivative of sine becomes cosine. We're going to leave that argument alone, left unchanged. But then I have to multiply by the derivative of the inside argument. And here now comes another product rule. So I'll use parentheses. The derivative of the first is 1 times the second, or y, plus the first times the derivative of the second. Well, the derivative of y is 1, but again, it's a y, so it's 1 times dy dx. All of that came from product rule. What does that equal? The derivative of 2x, which is 2. And I don't need to say 2 dy dx here because it's not 2y, it's just 2x. I'm writing the derivatives with respect to x. When I see an x in the equation, there's no need to worry about that extra little piece. Now, at this point here, we want to try to get dy dx isolated. So what if we divide both sides by cosine xy? Let's divide this entire thing by cosine of xy, which means I've got to multiply or divide the other side by cosine xy. So cancel, cancel. And now I have y plus x dy dx equal to 2 over cosine, but cosine in the denominator would just be secant. So I have 2 times the secant of x times y. So then subtract y would be the next step here. And then finally, to solve for dy dx, let's divide everything by x. So it's going to be kind of a interesting looking formula. Dy dx equals 2 times the secant of x times y minus y all in the numerator, and that's going to be divided by x. And that's my formula for the derivative dy dx. Number 3. Feel free to pause the video and try this one on your own. See if you can get that one right. And I'll try my best to work this one out a little bit quicker. Let's find the derivative. Another product rule here to begin with. So find dy dx. Let's begin. 3x squared derivative of the first times the second plus the first times derivative of the second. And there's a y piece, so I need the chain rule, dy dx. Derivative of 2x is 2, simply equal to 0. So 5x cubed y to the 4th dy dx is equal to, subtract the 2, subtract 3x squared y to the 5th. And then final answer here would be dy dx is equal to, again, negative 2 minus 3x squared y to the 5th, all divided by 5x cubed y to the 4th. So now let's put this into action here. We've done all these different implicit differentiation formulas. Let's look at part B and part C to wrap up this lesson today. Find the equation of the tangent line at 1, 2. Whenever we're asked to find the equation of a tangent line, we always need 2 things. So always need 2 things. And those 2 things are, thing number 1, we need a point. And thing number 2, we need a slope. Fortunately, the point's given to us. I'll check that off right away. The point's 1, 2. And the slope I can compute if I knew what the derivative formula was. And fortunately, I did all that work back here in part A, so I know that dy dx is given by this formula. So what we want to do is compute or evaluate dy dx at the ordered pair 1, 2. And this notation that I'm using right here is some just fancy notation that'll kind of help me organize where I'm inputting the coordinates. So 1 goes in for x, 2 goes in for y. So that will become negative 2 minus 3 times 1 squared times 2 to the 5th, all divided by 5 times 1 cubed times 2 to the 4th. So compute all that, and we should end up with a value of negative 98 divided by 80, which reduces to negative 49 over 40. There's my slope. So take the slope, take the point, and let's write our equation in point slope form. So y minus 2 equals the slope m times x minus 1. There's the equation of the tangent line. And finally, what about the equation of the normal line at 1, 2? Normal just means perpendicular in mathematics, and perpendicular slopes have opposite reciprocals. So I want the same ordered pair, 1, 2, so y minus 2 equals, but now I want the perpendicular slope. So rather than negative 49 over 40, we're going to take the opposite and the reciprocal. Positive 40 over 49. That's the perpendicular slope, or the normal line. So here are some examples, once again, of implicit differentiation and the steps to finding them. I hope you can use these examples and use the steps to sort of help you keep track of your terms. They do demand practice, and there are plenty of details and plenty of places to make errors. So work carefully, work cautiously, and make sure you put forth a lot of practice in writing implicit derivatives moving forward.